In this AstroPictionary Math problem, we would like to go over radiometric dating, specifically carbon dating with a mass containing carbon-14. We're given 10 grams of a substance containing carbon-14 radioactive atoms, and we're also given the carbon-14 radioactivity half-life of 5730 years. We would like to find the mass that is still radioactive after 3 half-lives. So after 3 half-lives of time has passed, how much of the 10 grams in grams is still radioactive? So our units at the end should still have grams in it. We have two equations. N is equal to N0 e to the minus lambda t, and we have the half-life equation related to the decay constant. T to the 1/2 is equal to natural log of 2 divided by lambda. We are also told that carbon-14 has 14 AMU, or 14 grams per mole. And we're also given Avogadro's constant of 1 mole is equal to 6.02 E23 atoms. First thing we need to solve for is the decay constant, which is equal to the natural log of 2 divided by the half-life. And that is equal to the natural log of 2 dividing by 5730 years after substituting in for half-life. So we need to solve. So we plug in natural log of 2 in our Google calculator. We divide it by 5730, and we're going to get 1.2 times 10 to the minus 4th as our answer. So now we know our decay constant. And don't forget the units. Decay constant has units. It is 1 over year. Now that we know the decay constant, we can use our N is equal to N0 e to the minus lambda t equation to solve. So we've got N is equal to N0, so I'll just put my equal sign here. N is equal to N0 e to the minus lambda t. Now we're not given N. We need to get N. So let's go ahead and erase it. We're given mass. The initial mass that we're given is 10 grams. Now we know we want to end with mass, so I'm going to put mass over here, M. Now we need to get out of grams. We're given that carbon-14 has 14 AMU, or 14 grams per mole. So all we do is divide by 14 grams, and we put 1 mole at the top. Now we need to get out a mole. Well, we're given Avogadro's constant, and Avogadro's constant is 1 mole is equal to about 6E23 atoms. Now what we do to the right-hand side, we have to do to the left-hand side, because we want to solve for M. But if you notice on the right-hand side, if we take away our units, we get grams, grams, moles, moles. We're left with N0. We're not left with N on the left-hand side. We want M, not N. We want mass. So what we did to the right-hand side, we need to do to the left-hand side. Is 1 mole divided by 14 grams. And the same thing with Avogadro's number. 1 mole is equal to 6E23. Now let's divide out letters and numbers to make things simpler. Grams goes out with grams, moles goes out with moles, and we're left with atoms over here. We got moles goes out with moles, and notice we have 14 on the left-hand side, 14 on the right-hand side, and we can eliminate this gram. With that gram, and 6 times 10 to the 23rd and 6 times 10 to the 23rd. Now we're just left with M is equal to 10 e to the minus lambda t. The reason why I did this is because You can write it as n is equal to n0 e to the minus lambda t. Or you can write it as m, if you're given units of grams, is equal to m0 e to the minus lambda t. Since we're given units of mass, we don't really need to change our format of our equation. We want to solve for m. So m is equal to m0, which is 10 grams. And then all we have is our e to the minus lambda t. Our lambda, we already have up here, 1.2 e to the minus 4. And our units are 1 over year. And then we need our time. And our time is 3 half-lives. 3 half-lives. So we have a 3, and then we have 5730. Don't forget your units, because we want the exponent to be unitless. So let's cancel out our units and solve. So we need e, clear it. Exponent is inverse e, there's your e value, parentheses, and then we have minus 1.2 e to the minus 4, multiply it by half-lives, which is 3, times 5730. And we close parentheses equals. Now we have our value, 0.12, and all we have to do is multiply it by 10. Multiply it by 10, and we have 1.27 left over. We started out with 2 digits, 0.0 or 3 digits, so we have about 1.27 grams left over. Let's just do a mental calculation. So we started out with 10 grams, and then we went through 1 half-life where we lost about half. Then we went through a second half-life where we lost about half. Then we went through a third half-life where we lost about half. So we should end up with a value of around 1.25. And we are very close to it, so our mental math worked out. Let's go to our graph. After 3 half-lives, we should be left with 12.5% radioactive atoms. So if I have 10 grams multiplied by 0.125, I should be left with around 1.25. And sure enough, we have 1.27. It's a little higher because it is an exponential graph, not a linear graph. So we're putting linear values down, approximately linear values down, but it's an exponential graph. These numbers here are approximate numbers.